All right, so today we're going to do something really cool. We're taking a classic piece of radio hardware, the SWR meter, and giving it a major 21st century upgrade. We're going to transform this simple offline tool into a smart, internet-connected device you can check from literally anywhere in the world. Let's dive in.
You know, it really all boils down to this one simple question. If you're a radio operator, you know that the health of your antenna system is everything. Is all that power you're generating actually getting out there, or some of it reflecting back, which could potentially even damage your gear? That's the exact problem the SWR meter was designed to solve.
Okay, so here's our roadmap. We're going to start with a basic, totally offline meter. Then, we'll get into the physics of how it actually works. After that, the fun really begins. We'll add an internet brain, build a server to catch the data, talk about the right way to send that data, and finally, reveal the complete global monitoring system we've built.
First things first. Before we even think about connecting to the internet, we need a solid foundation. So, step one is building a really capable, standalone SWR meter. The heart of this thing is just a simple Arduino microcontroller, which gives us a ton of flexibility right from the get-go.
And right out of the box, this base unit is surprisingly powerful. It's got 3 different modes. It can give you a live instant reading of power in SWR. It can also hold the peak power reading, which is fantastic for single sideband operators. And it has this really clever audio tone mode, which you're going to love.
And this quote just hits the nail on the head. Imagine you're up on a windy roof trying to tune your antenna. You can't be looking at a meter at the same time, right? Well, with audio tones, you don't have to. You can just listen. A low, slow beep means your SWR is getting better, while a high-pitched, fast beep tells you you're going in the wrong direction. You can literally tune your antenna by ear. It's genius.
So how in the world does a little circuit actually see invisible radio waves? Well, it's not magic, it's just some clever physics. It all comes down to a piece of hardware called a directional coupler, or a reflectometer.
Now, before we get into the nuts and bolts, let's just quickly define what we're even measuring here. SWR, or standing wave ratio, is really just a measure of efficiency. The garden hose analogy is absolutely perfect for this. You want all the water, in our case, the radio power, to just flow right out the end of the hose. But if you put your thumb over it, you create a mismatch, and water shoots back at you. That reflected power is exactly what we're trying to measure and minimize.
Okay, so check this out. Inside the meter, you've got the main line carrying all the power from your transmitter. Running right alongside it are 2 much smaller lines. These act like little spies, sampling a tiny fraction of the power going forward to the antenna and any power that might be reflecting back. A couple of special diodes then turn those RF samples into simple DC voltages, which the Arduino can easily read and then, boom, do the math to calculate your SWR.
All right, our offline meter is built. We understand the physics behind it. Now for the really fun part. It's time to connect this thing to the internet and evolve it from just a local tool into a global sensor.
And the hero of this entire upgrade is this incredible little chip, the ESP8266. It's a surprisingly powerful microcontroller that costs just a couple of bucks, and, this is the crucial part, it has Wi-Fi built right in. This little guy is the perfect brain for our new smart meter. Now you might be thinking, oh great, getting it online is going to be super complicated. But check this out. In the code, all you do is include the Wi-Fi library and then use one single command, wi-fi.begin, with your network name and password. That's it. That is literally all it takes. The device is now ready to talk to the internet.
Okay, so our meter is on our Wi-Fi network, and it's taking measurements. But where is that data going? Sending it out into the void doesn't do us any good. We need a destination, right? We need a server that's listening for this information and knows what to do with it. We need to build our data a home.
And for a server, we're not going to build some huge, complicated thing. We're going to turn to Python and this wonderful, lightweight framework called Flask. With just a handful of lines of code, we can spin up a simple web server on a laptop, a desktop, even a tiny Raspberry Pi that just sits there and listens for data from our SWR meter. So, every few seconds, the ESP8266 takes its latest readings and packs them up into this neat, universal format called JSON. You can see it's just clean, human-readable text. We've got the SWR, the power, and a device ID. It then sends this little package off to our server's address using a standard HTTP post request. And just like that, the data packet arrives at our Flask server. The server sees that same JSON package, pulls out the values, and then it can do whatever we want with them. In this case, we're logging them to a database with a timestamp. The journey from the antenna all the way to our database is now complete.
So we have a fully working system. We could stop here. But in the world of IoT, just working isn't always good enough. We're sending lots of small, frequent updates. So we have to ask ourselves, is the standard protocol of the web, HTTP, really the best and most efficient tool for this job?
So let's compare them. Think about HTTP. It's a request-response model. It's like making a phone call, saying one sentence, hanging up, and then having to dial the number all over again for the next sentence. It works, but it's a lot of overhead. MQTT, on the other hand, uses a publish-subscribe model. It opens one connection and just keeps that line open, letting tiny, efficient messages fly back and forth.
And if that last slide didn't convince you, this chart absolutely will. To send just 100 small data readings, the total amount of data used by HTTP is over 0.5 MB. Why? Because of all that connection overhead over and over again. MQTT, which was designed for exactly this kind of thing, uses less than 1/10 of that. I mean, it's not even a fair fight.
And this is the whole point. In the Internet of Things, efficiency is absolutely everything. Whether you're trying to conserve battery life on a remote sensor or just trying to be a good citizen on your network, MQTT's lightweight design is purpose-built for this kind of work. It is clearly the right choice for our smart meter.
Okay, so let's step back and put all of these pieces together. We built the hardware, we connected it to the cloud, and we chose the most efficient protocol for the job. So what do we have at the end of the day? What we have is a complete intelligent monitoring system. You can check your antenna's health in real time from your phone, no matter where you are in the world. All the data is logged, so you can track your antenna's performance over weeks, months, or even years. And, maybe most importantly, you can set up automated alerts. You can get a text if your SWR suddenly spikes, letting you catch problems before they become catastrophes. You're no longer reacting to problems, you're proactive. We've taken one piece of classic analog hardware and made it smart. And this is such a powerful idea that you can apply to almost anything. So the final question really isn't for me, it's for you. What trusted old-school tool in your world is just sitting there waiting for its own IoT upgrade?